we know how to find Laplace transform of a function and the inverse Laplace transform of a function. So in this, we can learn how to use those concepts to solve certain type of differential equations using the Laplace transform method. So solving differential equations, solving differential equations using Laplace transform, Laplace transforms. So these are like kind of interesting technique, and then you can compare this method with undetermined coefficient method and other technique. So for certain problems, you can get the answer much faster. So that's a kind of good news. So uh, so the first thing we need certain tools that we want to use for this one. So one of the tool is we need to know how to transform a derivative, because if you look at a differential equations, that means you have derivatives in there. So the problem is how to transform a derivative. So let's talk about that first. So transform of derivatives. Transform of derivatives. So let's say, so we're gonna say, so I'm gonna give this as a theorem. So it's a kind of interesting results. So what is that? So let's say suppose ft is differentiable, if it is differentiable, that's the first condition, and of exponential order, and is of exponential order, exponential order, exponential order. That is, the function, the absolute value of the function is bounded by m e c t for some m and c. So what happened in that case? So if under this condition, so we know that so the Laplace transform of the function ft exists under these conditions, exists, and we also have one interesting result, and the limit when t goes to infinity, e to the minus st ft, because it's exponential order, so that means the exponential function is bigger than that, so but this is negative sign, so that means this is going to be 0. So we can use that fact because we need to know what is the limit when t goes to infinity when you try to find the Laplace transform. So we can use that fact. So now what happened in this case? So then we can prove that the Laplace transform of the derivative, Laplace transform of the derivative f prime is simply s times the Laplace transform of the original function and then minus f0, So you have to be careful what this 0 means, because you know, we loosely say that, but if you look at the actual function, this function need not to be differentiable everywhere. It should be, if it is piecewise differentiable, that would be enough. So that means if you look at the graph, so there may be a situation like this. So so function go like that at that point, but here it can be like this. So this is fine. So that means so this is the function f. So it has to be piecewise differentiable. So So that means it is 0 or 0 plus. So it's kind of, because we're going this way, so it's not need not to be 0 but 0. So what we need is actually f0 plus. So that's the best one, but that's too much technical, but that's the actual idea. So this is the result. So you can see that if you look at the derivative, we're gonna get that, and then this gonna give you all other derivatives, because we can extend, we can substitute, we can replace f prime by f double prime. So then we're gonna go to the next one. So let's see how to prove this one first, and then we're gonna use this result to get the other ones. So let's prove this. It's a kind of very interesting argument. So let's look at the proof. So the proof, so we can start with the definition. So the Laplace transform of f prime t, so by the definition it is 0 to infinity e to the minus st f prime t. So what we're going to do is we're going to use the integration by parts here. So what are the candidates? So we know that u we can pick as e to the minus st, so that's the u function, and the rest of the function we're going to pick as the dv part. So that means dv is e to the minus I'm sorry, it is e to the so we can get that part. So it is e to the, it's not e to the, it's dv is f prime t dt. Now what we can do, we can get the derivative. So it's a du is, it is simply minus s, because s is a parameter like a constant, minus st dt. And then here if you take the derivative, because if you take the integral because the derivative, you're going to get ft back. So that's what you get. So that's all the 4 ingredients. Now we can use the integration by parts formula and substitute. So once you do that, what's going to happen now is it is uv. So that means it is e to the minus st gt. I'm sorry, it is e to the minus ft, e minus st ft, and then we have the limit going to go from negative infinity, 0 to negative infinity, and then because the minus sign, this become plus, and then we have the rest of the integrals, so 0 to infinity. So we have s e to the minus st ft dt. So that's the VDU part. Now we're gonna think of the results. So we know that because of the exponential order, so when you look at the infinity limit, we know that this has to go to 0, because that's one of the conditions. Because the exponential order, that means when t goes to infinity, the product goes to 0. So that means you're gonna get 0 from the infinity limit, and then when you plug in 0, what will happen? When you plug in 0, you can see that e to the term goes to 1, because we plug in t equals 0, and ft gonna give you f0. So here we assume that it is actually the left limit, the 0 plus, but we can write like that. And then we can pull s out. Once you pull the s out, it's 0 to infinity e to the minus st ft dt. And then you can see that this is nothing new. This is just the Laplace transform of the ft function. So that means we have a formula. So formula becomes it is s times the Laplace transform of ft, the original function, and then minus f0. So that's what you get as the formula. So it's a very simple proof, and that's what happened for the first derivative. Now what we can do is we can use this formula to find the Laplace transform second derivative, because what you want to do is simply replace f by f prime. Okay, so if you do that, So we can say for f double prime, we can have like that. So we can say f double prime ft is simply Laplace transform double prime ft is simply what we can do. We're gonna replace the formula. So what we simply replace f by f prime t. So if we do that, then what's gonna happen here is s Laplace transform of f prime t and then minus f prime 0. Now what we can do is we can substitute for this one because we already know this part. So we can substitute for that. Once we substitute for that, it is s. This is simply s Laplace transform of ft. So we can use the previous formula minus f0 and then minus f prime 0. So now if you simplify, you're going to get s squared L ft and then you have minus sign s f0 and then minus f prime 0. So you can see and again it all brings back to the function f and its derivative. So we can notice few things. So one thing we can notice is we can see the first term has a positive sign. You see, first term has a positive sign, everything else is negative. So you can see this is negative and these are all negative. So and that pattern gonna carry over. So the first term is positive, all the other terms are negative. So now what we can do is we can have like a kind of table so that we can use them for the future. So let's have a kind of table of derivatives. So so what's a table? So what you need to have in the table is, so you need to have the ft function here. So that's ft function, and this is the Laplace transform of that. So which you can write as fs. Okay. So let's have few here. So the first one is we're going to start with f prime t. So what's the Laplace transform of that? It is s times fs minus f0. So the next one, f double prime. If f double prime, it is s squared, that's matched the derivative term, and fs. And then what's going to happen is what we have s, so the s powers goes down, and then we're going to start with f0 and the derivative term goes up, so f powers goes and then all negative, and then so there are no any more s, so this becomes f prime 0. So you can see if we start with f0 and go to prime, so can you guess what is the third derivative going to be? So it is the third derivative is simply s cube fs and then goes down, so it becomes squared. We're going to start with f0 and then minus s f prime 0. We have one more minus f double prime 0. So that's what happened. So using the pattern, we can write a formula for the general one. So fn has to be, now you can see, is s to the n power fs. Everything else is negative, so it is s in minus 1 f0, and then keep doing all negative. At the end you're gonna get n minus first derivative evaluated at 0. So this is the g's f function. So like that. So those are the formulas. So you can see it's not very difficult to remember. Few things we notice. So these are the few things that we notice. So we notice that the derivative term and the Sn power, they have the same number. So it's a third derivative, third power. and then we see that the first terms are positive and all the other terms are negative. Everything else is negative. All of them. Everything is negative. And then you can see how we write the powers. You can see everything start with F0. All of them start with F0. So this is F0, F0, all of them. And then the next derivative like that. So after F0, then we have F prime 0. All of them, and then it's always gonna go up to one more derivative. So you can see if it is the first derivative, start with the function. Second derivative, you stop with the first derivative. If it's a third one, you stop with the second derivative, and then if you have nth derivative, you stop at the n minus first derivative. So it's only one less. So this is the table of Laplace transforms, and this can help you to solve certain differential equations. And also it is very easy to remember, only the first term is positive, all the other terms are negative, and then you say the power of s match with the derivative term, and then it's always end with one less derivative. So if it's a third derivative, you stop with the second derivative, and everything evaluated at 0. Okay, all evaluated at 0. That's also important. So all evaluated at, so you can see evaluated at, all evaluated at 0. I mean, if it is correctly 0 plus. Okay, so because we don't need to have a function which is continuous at 0. It's only need the left continuity. So it's only at 0, but we just put 0 there. But if you think about graduate level class, then we actually need to worry about exactly what happened at 0. But in this level, we just say 0. But please keep in mind, we need the left continuity at 0. Okay, at 0. So if you have something else, you probably need to transform the problem to some other values. Okay. So we have all the tools we need. So now the next thing is we're going to see how to solve differential equations using Laplace transform method. So let's go for that. That's the interesting part. So solving in this case we're going to say only ODEs, solving ODEs with Laplace transforms, with Laplace transforms, with Laplace transforms. So let's start with something easy. So I'm going to start with a first order differential equation and see how we can do that. So let's do the first example. So it's example number 1. So let's say solve y prime plus 4y equal to t minus 3. 2t minus 3. It's a first order, so you need one initial condition. So if you want to solve completely, so let's say y0 equal 1. You can just put some numbers here. So now if you look at this problem, how many ways are there to solve this one? So you can see this is first order linear, so you can use the integrating factors, and also you can use the undetermined coefficient method, and we also know the series solution method. So there are series solution method, and then the new one, the Laplace transform method. So there are 4 ways to solve this particular problem. So let's use the Laplace transform method and see how it gonna turn out. So the first step is, once you get the differential equation, we're gonna take the Laplace transform and convert the whole equation into the Laplace domain, so S domain. So let's do that. So that's the first step. So the first step is take the Laplace transform of both sides. So you can say taking the Laplace transform, taking the Laplace transform So if you take the Laplace transform, what happened? It's a Laplace transform of y prime plus 4y equals Laplace transform of 2t minus 3. So we take the Laplace transform for both sides. But we know that the Laplace transform is linear. So because of that, we can write this one as, we can separate them. We can say Laplace transform of y prime plus the Laplace transform of 4y on this side. And on the other side, the same thing. We can split it, so we can leave it like that. Or you can write it. So let's say 2t and then minus the Laplace transform of 3. So we have that. Now what we can do is we can find the Laplace transform each and every term. So the first one, we can use the formula. So according to the formula, this is the Laplace transform of y prime. So we can use the formula. So what the formula says, it says that, so we assume that the Laplace transform of y is ys. So if you assume like that, then we can see that you're going to get s, ys. So you always do that. That's the kind of convention. We're going to use uppercase letters for the Laplace transform. And then minus, we have y0. That's what you get from the first term. Okay, so this all get the first term. And then for the second term, what we have is 4 is a constant. We can pull it out. Then we have Laplace of y, so which is, we write like that. It's the same ys. Now let's look at the other two terms. We use a table, and from the table we know that this is 2. Laplace transform of t. What is Laplace transform of t? It is 1 over s squared. So we're going to say 1 squared minus 3. 3 is a constant, so we're going to say 3. And the Laplace transform of 1 is 1 over s. So that's what happens. So this is simply coming from the table. It's a table. Now let's plug in what we know. So we know a few things here. We know y0. Y0 is what? Y0 is 1. So if you plug in y0 is 1, and also if you combine these two terms, you can see that you can combine these two terms because they have the exact same y term here. So if you combine them, you're going to get s plus 4 ys, s plus 4 ys, and then we have minus y0. How much y0? Which is 1. Is given. That's given. And then here we have 2 over s squared minus 3 over s. Thus we have. Now what we can do is we're going to solve for ys. So after we substitute for all the terms, what we're trying to do is solve for ys. So that's the next step. So what we're going to do, solve for ys. Solve for ys. So to do that, I'm going to move the one term to the other side, and then we can divide by s plus 4. So that's what we're trying to do. So let's do that first. So what we have is, we have y. I'm going to write this first. I'm going to bring the 1 to the other side. If you bring 1 to the other side, we're going to have s plus 4 ys equal, if you bring 1 to the other side, it is 1 plus 2 over s squared minus 3 over s. So there are a few things now. There are two ways to proceed from here. So the one way to do that is, we normally leave these terms like that. The reason is, when you divide by s plus 4, you're going to get 1 over s plus 4. The inverse of that we already know. So that means there are no problems with that. What we normally do is, we only simplify the other two terms. You simplify those two as one single fraction and then divide. So at this level, there are two steps. Okay, so if you simplify that, if you simplify all of them, that's one way. The other way is you simplify all the fractions. So what I'm going to do, I'm going to take the common denominator. So if you take the common denominator, in this case, you can see the common denominator is s squared. So in the first term, what is missing is s squared is missing. The second one is there's nothing missing, but I'm going to write that at the end.
and from the last term you can see that one s is missing. That means you're going to get 3s, and then we have that 2. Okay, so that is write as a single fraction. So write as a single fraction. So sometimes this is going to help you. Okay, so write as one fraction. Okay, so that's like kind of helpful step. So we're going to get to 1. Now what we can do, we can divide by s plus 4 both sides. So we can divide. So once you divide, you're going to get ys equal, so what we have is s squared minus 3s plus 2 over s squared s plus 4. So we solve. So actually it's like almost done, because what you did is you solve the problem in the S domain. So this is what we call solve the problem in S domain, Laplace domain. Okay, so solved the problem in S domain. So now what you want to do? You want to transform that back into the time domain. To do that, what we're going to do is we're going to find the inverse Laplace transform. Okay. Now what we need to do is, so we need to find the inverse Laplace transform. So we can say what is left. What left is to invert. We can invert this. So how to invert? We can use the partial fraction method that we learned in the previous lecture. So we can use the, so we can say we use partial fraction method. We use partial fractions method. So let's do that. So we can write the form first. So it is s squared minus 3s plus 2 over s squared s plus 4. Now we have, this is like s squared, that means it's a repeated root. That means it has to be a over s plus b over s squared, because we know that this follows the form of the smallest one. And then what we have is plus, this is s plus 4. When you have s plus 4, it is linear, that means this has to be a constant, so it is c. So the goal is to find a, b and c. So what we're gonna do is we normally use the standard technique. We're gonna multiply both sides by that. So that means we're gonna get s squared minus 3s plus 2 equal a times the missing terms. Missing term is s and s plus 4 plus b. The missing term is s plus 4, and then plus here the missing term is only s squared. So now the goal is to, what we normally do is we can use a substitution technique, because that's much faster. So you can see, to find a, we're gonna see what is common to the other two, and you can see there's nothing common to the other two. So that means you cannot find a directly first. So what we're gonna do, we're gonna find as much as you can first, and then you try to go for a. So you can see, if you look at b, if you look at the other two terms, you can see that s is common to the other two. Since s is common to the other two, what we're going to do is we're going to say that equal to 0. So let's do that. So you can see substitute. We can say substitute s equals 0. If you do that, then you're going to get, what do you get? You get 2 equal, if you substitute s equals 0, this term is gone. So if you substitute b, and if you plug s equals 0, you get 4 plus 0, and this says that b has to be 1/2. So we get the value of b. So let's do the same thing. Now you can see that there's there's something common to the first two terms. Let's mean s plus 4, so that means we're going to plug in s equal negative 4. Just so I can say opposite value. So s equal negative 4. Once you do that, and you can see that you're going to get 16 here, and then negative 4. So you're going to get 12, and then plus 2 equal negative 4. That means this is 0, this is 0. You get c times 16. So now you can find c from here. So how much you get here? So it is 16 times 12, that means 28. So 30, so that means C is simply 30 over 16. If you simplify this, is 15 over 8. Good. Now the question is how to find A. So you can see that you can, the one way to find A is just plug in something else. Don't plug in 0, don't plug in negative 4, just put something like 1 or something. That's a much quicker way. The quicker way is we're gonna go to the coefficient now. So what we normally call, we use the hybrid technique. What's a hybrid? You're gonna use a substitution as much as you can first, and then you think of equating coefficients. That's much faster. So we're gonna go with the always go with the highest possible coefficient in the equation. So you can see the highest possible coefficient, highest possible term is in s, you get s squared. So we're gonna go with that. So we're going to say coefficient of s squared. Always go with the largest term. So in this side it is 1. And you can see how to get a squared term. You can see to get a squared term, you need to multiply these two. So if you multiply those two, the term going to be a squared. So that means the coefficient is simply a. The same argument. How to get s squared term? That's only way. This is the only way you get the squared term. So that means the coefficient is simply c. Now, since we know the value of c, we can plug in that and we can find a. So that means this says that a is simply 1 minus c, which is 1 minus c is 15 over 8. So that means you're going to get negative 7 over 8. So we find all three now. So once we find all three, what we can do is we can plug in them back into the equation. So that means your ys now going to be, what is ys? Just plug in the values. So a is negative 7 over 8, 1 over s. And then b is 15 over 8, 1 over s squared plus c. C is no, that's not B. B is 1/2. So B is 1/2. So you're gonna get B is 1/2 here, and then you're gonna get C, which is 15 over 8 times 1 over S plus 4. So you can see that this is the ys. So you write ys as a partial fraction. Okay, so ys you write as partial fractions. So that's the partial fraction decomposition. So partial fractions. So we found. Now what we're gonna do, we're gonna invert, because we know that the inverse of all these terms we know. We know what's the inverse of that. That's 1. This is just t. This is the exponential function. So we're gonna use that. So we're gonna invert and get the solution. So let's do that. That's the last step. After that, by taking inverse Laplace transform, we also know that that's linear, so that means we can take the inverse of each and every one. So that means your answer yt is simply the inverse Laplace transform of ys. So what we can do, we can do term by term and pull the constant out. That means negative 7 over 8, that's a constant, and take the inverse of 1 over s, and then pull the constant out, take the inverse of 1 over s squared. Same thing, pull the constant out, and then take the inverse of 1 over s plus 4. Now what we can do is we're going to go term by term. 1 over s means 1, so you're going to get negative 7 over 8 plus 1 half. 1 over s squared means t, and then plus 15 over 8. So you can see L inverse 1 over s plus 4. So that was a formula. Remember, when you take the Laplace transform of e to the minus at, it's going to be 1 over s plus a. That's exactly the case. So you can see in this case a is 4. If a is 4, so you're going to get e minus 4 times, and then we have t. So that's the formula. So that's the answer you're going to get. And then so that is the solution to the non-homogeneous differential equation, first order differential equation. And then you can see that initial conditions have been taken care of automatically. So that's one of the interesting thing about this one. You don't want to deal with initial conditions separately. So I'm going to write this as a note. So you can see that the initial conditions initial conditions initial conditions have been have been taken care of automatically. Have been taken care of automatically. So that's really interesting. Okay, so that's about how to solve a differential equation, first order differential equation using the Laplace transform method. So let's solve maybe one more, but what we had in this problem is on the non-homogeneous part you had just a linear function. So what if you have a, let's say, exponential function? Let's talk about that. So let's say you have a exponential function on the other side. So let's see what's the difference. So let's do the next example. So which is, let's say, solve y prime minus, let's say, 2y equal 3 plus 4 e to the 3t, have some initial condition y0 equal 1. This is just a matter of get a constant, and maybe sometimes it can easily solve. So that's the one. So again, as we did before, we just take the Laplace transform. So let's do that. Take the Laplace transform of both sides. So let's do that. Once you do that, what do you get? From the first term, you're going to get s times ys minus y0 minus 2 times y becomes ys. 3. What is 3? 3 becomes 3 over s. We know how to do that now. Plus 4 times. Okay, so we need to use the shift theorem. So we have e to the 3t. So in this case, we always go with the opposite sign. So that means it's going to be simply s minus 3 because it's a plus 3. So it's become minus 3. It's always opposite sign. Okay, so that's what you get, and you can also simplify this a little bit. So it's always a good idea to simplify this. Take the common denominator. So if you take the common denominator, what's going to happen? You just need to cross multiply them. So you're going to get s times s minus 3. So if you cross multiply, what you're going to get is you're going to get s minus 3 times 3. So this is simply just the cross multiplication. You have 3 s minus 3 and then plus we had 4, so the 4 times s. So it's just a simple cross multiplication. So how those numbers works? So we're going to multiply this way and that way, and it's going to give you the top term. So you can see that you're going to get, what do you get? You're going to get 7s minus 9. That's what you get. So that means you can see that so we're going to plug in the other values that you have. So if we plug in, we know y0 equal 1, so let's prove that. So that means you're gonna get uh, if you combine, you're gonna get s minus 2 ys, and you can move that term to the other side, so you get 1 plus 7s minus 9 over s times s minus 3. That's what you get. And then we divide both sides by s minus 2, so we divide by that. So that means ys is simply 1 over s minus 2 plus, you can see here it is 7s minus 9 over, we have s and we have s minus 2 now, and also we had s minus 3. So you can see I did this in a slightly different way. I did not combine this term with the rest. The reason is when you divide, you're going to get 1 over s minus 2. We already know the inverse of that. So what you can do, you can leave that term there and find the partial fraction only of the other term. That's another way to do it. So it's just option, you know. So some people like that way. It's dependent on what you're going to do. Sometimes you can just combine into one term, or just leave it like that. Okay, so what I did was I did not combine. Okay, so did not. It's just a personal preference, so you may like it or you may not like it, but let's see how it's gonna work. So just see. Okay, so I'm gonna leave it like that, because when you wanna do the inverse, we already know what the inverse is, so I'm just gonna go with the other term only. So what you want to do is we need to invert this one, so we use the partial fraction. Okay, uh, so we can say using partial fractions. So what we have 7s minus 9 over s minus 2, s minus 3 equal, we can write all those different factors. So we have a over s, there's no order, just whatever order you like, b over s minus 2, c over s minus 3. Now what we normally do is we're going to multiply by the common denominator. So that means this is going to be 7s minus 9 identical to, we only write the missing terms. What's the missing terms here? A, the missing term is s minus 2 and s minus 3. Here the missing term is, one is s is missing, so s and s minus 3. And for the c, s is missing, s minus 2 is missing. Okay, so after you get to this level, there are two ways to do it. One way is just substitute the appropriate values. For example, if you want to find a, look at the common terms of the other two. You can see s is common, so that's, you're going to make 0. That means you plug in s equals 0. Right after you plug in s equals 0, you get a. The same argument if you want to find b, look at the other two terms, see what is common. So s minus 2 is common, that means you plug in s equal 2 to get b. And if you want to find c, look at the other two terms, you can see s minus 3 is common, so you plug in s equal 3 to get c. So that's it, very simple. So let's do that now. So we're going to go with that. So we're going to say s equals 0 first. So we're going to substitute s equals 0, and once you do that, you're going to get negative 9 equal, so identity become equal now, and the 8 times negative 2 negative 3, this is going to give you a. So you can see a is simply negative 9 over 6, that means negative 3 halves. Good. And then to find b, you can s equal 2, so you're going to substitute s equal 2. So once you do that, you're going to get 14 minus 9, so it is 5 equal, you're going to get, what do you get? You get 0. You're going to get, we only get the b term is only one left. So yeah, actually if you want to see that, I can probably slightly modify this part. So what happened above is only the first term you get, other terms are simply 0. So that's what happened. So this can give you a is negative 9 over 6. So that means negative 3 halves. The same idea. First term is 0. You're gonna get the b. You're gonna get 2 times. If you plug in 2, you're gonna get negative 1 plus 0. You don't have to, but it's okay. It's clear. So you can see b is simply 5 over negative 5 over 2. So negative 5 over 2. And then to find c, you plug in a c equal 3. So you're going to substitute s equal 3. Once you do that, you get 21 minus 9, so it's just 12 minus 0 plus 0 plus c times we have 3 and plug in 3, that means 1. So this is going to give you the value of c, which is 4. So here all three values, then we can write the ys. So what is ys now? We're going to plug in them. So we have don't forget we had a one more term up there. So we have that term is 1 over s minus 2. We already have that. And then we're going to plug in the values for this. So a is negative 3 halves 1 over s. Or, I mean, you can just substitute there. So you can write in either way. So I'm going to, since this is substitution, I'm going to write the other way. I'm going to put that up there. Because then you can see what's going on. Actually, you can put the negative sign here. But a is 3 halves, so I'm going to say 3 halves over s is kind of compact. And then b was negative, again it's a negative, so we can say negative 5 half over s minus 2. And then c was 4, so 4 over s minus 3. Now what you need to do is you need to simplify. You can see these two are the same. So that's the only extra step that you get if you do not combine at the beginning. If you combine, you don't get that because it automatically simplifies inside. But if you do not combine, you need this extra step here. After you find all those partial fraction of the other term, you have to combine and write as 1. So don't forget that. So that means if you combine them, what's going to happen is I'm going to write the positive terms first. So we have 4 over s minus 3, and then we have 5 half and 1, that means we got negative 3 halves, so we have negative 3 halves 1 over s minus 2, and then we have that s term which is negative 3 halves s. We just in this form because it's clear what you want to do. Okay, so we have the partial fraction. Perfect. Now what you want to do is just take the inverse of that. So let's do that. Once you take the inverse, so taking the inverse Laplace, we're gonna get yt, which is the inverse of ys. So simply take the inverse of each and every term. I'm gonna write this extra step here. So we have 4 s minus 3 minus 3 halves s minus 2 minus 3 halves s. So once you take the inverse, you simply end up getting the first one. First one says it is 4 e to the 3t because it's opposite sign. So opposite sign, so negative 3 become positive 3. And then we have negative 3 halves e to the opposite sign 2t. And then minus 1 over s, okay, it's not s, 1 over s. So 1 over s means 1, so that means you're going to get 3 halves. So that is the solution to the initial value problem because it has already been taken care of the initial condition. You don't have to do that extra. Okay, so those are two first order differential equations. So now let's try to look at a second order differential equation, see how it's going to turn out. So as the first example, so let's say so I'm going to write this. So solve second order, solving a second order ODE. Okay, so let's do that. So let's do this as the first example. So let's say solve x double prime plus x equal, let's say, 3 sine 2t. So this is second order, you need two conditions. So let's say x0 equal 1 and let's say x prime 0 are equal 3. Just put some conditions. Sometimes we just put 0 0, but let's try to see how it works like with some non-zero initial conditions. Okay, that's the problem, and we know that we can solve this problem using what we call the undetermined coefficient method. But here we try to solve this problem using the Laplace transform technique. So let's see how the rest of the things work. Always the first step is take the Laplace transform both sides. So take the Laplace transform. So once you do that, what's going to happen is the first term going to give you s squared sx. So that's the transform version of the solution xx minus s x0 minus x prime 0. So those are the terms that you get from the first term plus. So all these coming from the first term. So all these come from the first term. So now let's go to the second term. In the second term, it's just x, that just become sx. That's a transform version of that. Okay, so that side is over. Other side, we have to use a table. This is sine 2t to omega equal 2 in this case. So that means if you use a table, what's going to happen is, so we have 3 times s squared plus 2 squared times 2. So if you simplify, this is simply 6 over s squared plus 4. That's easy to write like that. Okay, now let's plug in the other values that we know. We already know that s0 equal 1, so this is 1. So we know this is equals to 1. And we also know that that's equals to y prime 0, x prime 0, which is equal to 3. So let's plug in them and try to bring it to the other side. So if you do that, what do you get? So you're going to get that here you can combine the first two terms. That means you're going to get s squared plus 1 times sx. That's what you get from these two terms. So if you look at these two terms, this and that, you're going to get this. And then I'm going to move the other terms to the other side. So that means minus s become s. So it's become s plus negative 3 become positive 3. So that's what you get from the first two terms once you bring to the other side. And you have 6 over s squared plus 4. The next step is we divide both sides by s squared plus 1. So that means your sx, the big one, is simply you divide, so become s plus 3 over s squared plus 1. That's the first term. Plus here you have 6 over s squared plus 1 and s squared plus 4. Everything looks good, and again it's up to you whether you want to combine this as one fraction or leave it like that, because we already know how to invert this one. So if you want to invert this one, what we normally do is we're going to split them into two. So maybe you remember that from the inverse Laplace transform lecture. So you can see we can split this, and right after that you can use the table and get the answer. So we already know that. So what you need to do is only handle the second one. So that's what we're going to do. But again, it's simply up to you whether you want to combine this into one and do it. Sometimes that's also helpful because it's going to simplify inside automatically. So maybe you get the answer faster. But it's just up to you. But here, what I'm going to do, I'm going to only look at the other one because we can handle this one later. So let's do that. So what I'm going to do, I'm going to take the partial fraction of the second one. So because we are done already, but in the S domain, but we want to find the solution in the T domain. For that, we need the partial fraction the invert. So let's do that. Uh, Good. So what we do, we're going to use the partial fraction. So use partial fractions. Again, I only look at the second term. So we have 6 over, what we have is s squared plus 1, s squared plus 4, that's what we have, identical to, we have s squared plus 1, this is the second order, degree 2, so that means we have degree 1. So it is as plus b, and this we have this is s squared plus 4 degree 2, so degree 1, so cs plus d. So always so this is degree 2, see this is always degree 1 less unless it is repeated, degree 1. Okay, so we have the right form. As before, we're gonna multiply by the common denominator, so we're gonna get as plus b. We have the other one, that means s squared plus 4, and here we have cs plus d, again the other one, so s squared plus 1. Now what we're gonna do, you can see that the substitution technique does not work. We normally do the substitution first, but unfortunately that doesn't work, so we're going to go with the coefficient technique. But when you do coefficients, we always go with the largest possible coefficient in the whole equation. So in this case you can see that largest possible term would be s3, s cube, so that means we're going to go with that. So we're going to go with the largest coefficient. So this is the coefficient of the largest term, that means s3. So there are no term here. Here you're going to get a is cube, though the coefficient is only a, and then you also get cs cube, so the coefficient is only c, just the coefficient. Go to the next smaller one, so it's the coefficient of s squared. No s squared term on the left side. How to get s squared term there? You can see when you multiply these two, you get a squared term. When you multiply those two, you get a squared term, and those are the only two. So that means you're going to get b plus d. Those are the coefficients of the squared term. And then uh, actually, we cannot do this if you just write an equal sign here. That's why we write the identity sign, because if you just write an equal sign, this argument does not work. Sorry. So go with the coefficient of s, which is 0 again. How to get an s term? You get s term if you multiply a's with 4. So that means the 4a is the coefficient. And to get a s term in the other one, you can see it is c. And then the last one is s to the 0 power or the constant term. So that's the constant term. If you get the constant term, you can see it is 6 on this side. Other side, the constant term is 4b plus the last one, you get a d. So the goal is to solve these 4. So there are 4 unknown, 4 equations. And you can see that this is not that bad. For example, if you subtract these two, you get a directly. I'm going to subtract the top one from the bottom one. Then you can see that you're going to get 0 equal 3a. Just subtract the two. And then this says that a equal 0. Then the top one says that c equals 0. Right there. And then do the same thing. What I'm going to do, I'm going to subtract these two. If you subtract those two, you're going to get 6 equal, d get cancelled, you get 3b. This says that b equal 2, and the second equation says that d equal negative 2. So we get all 4. Okay, very quick. So that's it. Now what we can do is we can substitute that into the formula, into the form. So once you substitute that into the form, what are you going to get? So you can see that a is gone, c is gone, only have b and d. So that means your partial fraction decomposition going to be, of the original one, going to be sx equal So you can see, and also remember we had a term that we did not use for the partial fraction. So I'm going to split that. So that means you can write this one as s over s squared plus 1, and then plus 3 over s squared uh, plus 1. That's what you get from the term that you did not use. Now the rest of the terms going to be, we say we got like b equal 2 and d equal -2. So if you plug in that, it's going to be 2 over s squared plus 1 and minus 2 over s squared plus 4. So you can see there are some slight simplification going on here. So you can see you can combine these two terms. So if you combine these two terms, you're going to get 5. So that means you simply get s over s squared plus 1 plus, we have 5 here. So 5 over s squared plus 1 minus 2 over s squared plus 4. These are very easy to invert. We already know that from the table. So use the table to invert. So that means your xt is simply the L inverse of xx. So let's go with term by term. So first one is simply the sine, omega equal 1. Actually, it's S means the cosine, because it's S. If you see S, it is the other one. So that's how we remember. So it's a cosine. So you're going to get the cosine t. And then the next one is you don't have S there. So that means that's a sine. And with the 5, it becomes 5 sine t minus. And then you can see that omega equal 2 in this case. So this omega equal 2, that's exactly up there. So that means this is simply going to be sine 2t. Perfect. So that's the solution to the non-homogeneous second order differential equation with two non-zero initial conditions, and you can see that all the initial conditions have been taken care of. So just for curiosity, let's see how the graph of this one looks like. Okay, so let's do that. The graph of this function is has this form. So you can see that it is not really a cosine or sine function. You can see that there is some distortion. For example, look at this part. So you can see there's a distortion. It's mainly because they have two different the two functions have different frequencies. For example, here the frequency is 1 because 1 times t, and then you can see there's a frequency 2. So since they have two different frequencies, it's going to distort the graph. So that's kind of thing that you can use. So we're going to use these kind of ideas in when we do what we call the Fourier transform, because the Fourier transform, and then if you try to write the Fourier series, actually Fourier series, what we do is we're going to combine a lot of functions like that, sine cosine function with different frequencies, and this kind of very nice idea. And in that you're going to see these kind of things there. Okay, so this is just one observation. It's going to distort the graph. It distort this regular sine cosine graph. Okay, so let's do another example. So as the next example, we're going to do this one. So let's say solve y double prime minus 3y equal to cosine, let's say square root 3t. Let's assume that the initial conditions are 0. So y 0 equals 0 and y prime 0 is also equal to 0. So both initial conditions are 0. So we can do as before, take the Laplace transform. So we can take Laplace transform of both sides. So once you do that, what's going to happen? This is a second derivative. So that means it's going to be s squared ys minus sy0 minus y prime 0, and then minus 3 times, this is just y, so it's going to be ys. That's the same ys. And then on the other side, what will happen, it is 2 times, this is a cosine. So when it's a cosine from the table, we know that it is s squared plus omega squared. So in this case, omega squared is 3, and then s goes there. So that's the Laplace transform on the right side, just coming from the table. So this from the table. Good. Now we're gonna substitute the values that we have. So you can see that this is 0. So this is 0. So and that is 0. So those two terms are gone. So you simply end up having s squared minus 3 times ys on this side, and here we have 2 times s over s squared plus 3. Now we know what to do. We can divide by the factor. You can divide by this factor. So once you do that, you're going to get ys equal to s over s squared minus 3, and then s squared plus 3. But you can see that this has a like kind of nice form. So this is the differential square situation. So you can write this one as 2s over s to the 4th minus 9. So now what we can do is we can we do this traditional method. So we use the partial fraction decomposition. So only thing that left is the so we can need to invert. So need to invert. So for that we use a partial fraction. So that means we can write the decomposition. So it is 2s over s to the 4th minus 9. And you can see that if you so this one has two factors, so, two zeros. So you can see that s equal plus or minus square root 3. Actually, we don't want to go in that route here. The reason is we already know a invert of that. When you have square minus 3, that is the hyperbolic sine cosine functions. So because of that, we are not going to go into two linear factors in this case. We can stay with quadratic. So that's a major difference. So we can write the first one we can write, so it is 4s, no, not 4s. So we can write this one as as plus b over s squared minus 3 plus cs plus d over s squared plus 3. So this is, so remember the format what we write. So second one is clear, but the first one we did not write into linear factors. The reason is we already know the form of the invert of those two, inverse Laplace transform of those two. So this is a different situation from the regular partial fraction method. So I'm going to write that. So it's a different from standard partial fractions. So yeah, please remember that how we did it. Okay, we're gonna make it easy, and then we after that we know what to do. We're gonna multiply by the both sides by the common denominator, and then we can find ABCD. Okay, so once you do that, so you're gonna end up getting 2s equal as plus b times s squared plus 3, and then cs plus d times s squared minus 3, and then we're gonna use those techniques to find ABCD. Okay, so let's do that. So what we have is we have 2s equal as plus b times s squared plus 3, and then we have cs plus d times s squared minus 3. Uh, so we can do two methods. We can use the substitution method, and also we can try the coefficient method. But when you try to use the substitution method, and you can see that the terms are s equal plus or minus square root 3. So you can plug in those values and try to try to write equations for that. But if you feel like that's difficult, what we can do is we can just use the coefficient method. So I'm going to use the coefficient method for this problem. Um, so we can start. We always start with the largest degree term. So you can see the largest degree that we get is s cubed. So when you multiply these terms, you get s cubed term. So we're going to start with that. So we're going to go with the coefficient of the s cubed term. So the coefficient of s cubed, and you can see there are no coefficient, no x cubed term, that means coefficient 0. And then here when you multiply a's with s squared, you get a s cubed, so the coefficient is a. And on the other side also, on the other one also, you get c s cubed, so the coefficient is c. Okay, that's the first equation. And then we're gonna go to the next smaller, so that means s squared, uh, no s squared term. And how to get a squared term? And you can see that you get a squared term when you multiply these two and those two. So the coefficient is gonna be b and then plus d. So those are the coefficient of s squared. And then we're gonna go to the next coefficient, which is coefficient of s. No, actually there's a s term here. So the s term, the coefficient is 2. And then how to get a s term? You can see when you multiply as with 3, you get a s term. So that means the coefficient is simply 3a. And the same thing, if you multiply cs with negative 3, you get a s term, that means negative 3c. So those are the s terms. And then let's go to the next one. So next one is x to the 0 or the constant term. So I'm going to say constant term. So constant term is 0. There are no constant term on the others. And then from the first one, you're going to get 3b. And then from the other one, you're going to get 3d. So those are the constant terms. Okay, now we need to think about how to solve this. Just look at the numbers and you see, try to use plus minus thing. Because when you have plus minus, when you add them, it's gonna make it 0. So that's what we're trying to do. So that means if you look at these two, you see that you can cancel the c term, but before that you have to multiply by 3. So what I do is I'm going to multiply the first equation by 3 and then add. So then you get 3c, negative 3c, they get cancelled. So you're going to get 2 equal 6a. Because 3a from the first one, 3a from the bottom one, because you multiply by 3 first. Okay, so this says that a equals 0, and then this implies that c equals 0 from the first equation. Okay, first equation says c equals 0. Similarly, you can go with the other one. We do the similar thing. We're going to multiply the second equation by 3 first and then add. Once you do that, you can see you're going to get 0 equal 6b now. This says that b equals 0, and the second equation implies that d equals 0. So we find all four. Okay, you can see that it's very simple. It's not that difficult even to find 4 coefficients. Okay, so after we get that, we can go back and plug in that in the equation. So we have ys, which is equals to 2s over s4 minus 9. It's a 4th degree. And then what we got is, you can see b and d are 0, so that means those two terms can go away. So only have a is 1/3. Since the fraction, we write it outside like that. And then s over what we have is s squared minus 3. 3 we write as square root 3 squared, because that's what we need. And then it's a minus 1/3. And then again the same idea is s over s squared plus square root 3 squared. And then for the first one, you can see that this is the hyperbolic cosine, and the second one is the cosine. Okay, so this is coming from the table. Okay, so look at the table, and table tells you that there's a cosh and the cos. So, okay, so perfect. And then what we can do is we can invert now. So so then we can say taking inverse Laplace transform. So we have yt, which is simply the inverse Laplace transform of ys. So you can see that the first one says that 1/3 cos. This is there is a sign, so that's the cos. So so you get square root 3t and then minus 1/3 cos square root 3t. Okay, so that's the answer for the differential equation. It's a second order non-homogeneous differential equation with zero initial conditions. Okay, let's look at the graph. So you can see that because of the cos function, we have like a different situation here. So the graph of that looks like that. So this is the situation. So what's going to happen? You can see that what is the small one? The small one says what happened in the first in the domain from 0 to 2, and you can see that it's exponentially grow. But if you look at the large domain from 0 to 9, and you can see that at 9 it go to 1 million. So it grows really fast in a small time. So these kind of solutions are what we normally call blow up solutions, because it's going to grow really fast. uh, so like for example, if it is a system, the system going to break at this moment, because if let's say this is energy, you try to write an equation for energy situation, and then this is what you get as a solution, and you can see that it's grow really fast. So normally it's gonna just be a blast at this moment, or gonna break the system. We normally call these blow up solutions, okay, because it's gonna grow really fast. So we're gonna say blow up solutions. Okay. Yeah, it's a kind of interesting idea. We can use these kind of things in display engineering. Okay, good. So so let's look at a situation where we're gonna see all like a three like a constant coefficient situation, but we have like all three type of coefficients. So let's see, because we only have two now. So let's look at the next example. So this one. So let's see. So say solve. We can have y double prime minus 2y prime minus 3y equal, let's say, 7 plus 2e negative t, and along with y0 equal 0 and y prime 0 equal negative 4. Okay, let's put some numbers. So let's see what's going to happen. Same idea. But do you want to look at the characteristic equation for this one? So what's the characteristic equation? It is lambda squared minus 2 lambda minus 3 equals 0. So that means the factors are lambda minus 3 and lambda plus 1. So right. So this says that the lambda values are negative 1 and 3. So lambda values are negative 1 and 3. But the thing is that you can see they match. Negative 1 match with the number here. So from the undetermined coefficient method, we know that in that case it's going to create a difficulty, because you need to find a linear independent solution. Because if you just try to assume the solution as a, e, negative t, it's not going to work, because that's also a solution. That means you need to introduce a t term into the formula, right, for the guessing term. So so the yp has to be, so what is yp in this case if you use the undetermined coefficient? So there's a constant term, that means there should be a, and then b, it is not just b e to the negative t, it is b t e to the negative t. So we had to introduce that extra t to find a linear independent solution. So now let's see how this comes out in the Laplace transform method. Okay, so let's see. So there should be a term like that. Okay, so let's do that. Now again, as before, we can take the Laplace transform. So taking Laplace transform, so we're gonna get s squared ys minus s y0 minus y prime 0, and then we have minus 2 times s ys minus y0, and then we have minus 3 times ys, that's what you get. And on the other side is a 7, so that means 7 over s, and then plus is e to the at. E to the at means it is, in this case, a equal 1, so the transform is 1 over s plus a is 1, so that means it's going to be 2 over s plus 1 according to the formula. So if you forget the formula, this is the formula we use. We know that there's a formula which is e to the eat function, remember? This eat function, which is simply 1 over s plus a. It's opposite sign. Good. Now we have the transforms. Let's substitute the values that we have. So this is 0 and this is also 0. So those two terms are gone. This is a negative 4. Okay, that's what we have. That means positive 4. Once you bring to the other side, it's become negative 4 again. So what we have is we have s squared. Let's look at the y terms, minus 2s minus 3. You see, this is simply the characteristic equation, but with s now, not lambda, but s. So that's the difference. And ys, now you're going to bring to the other terms to the other side. So we have negative 4 coming, and then we have 7 over s, and then plus 2 over s plus 1. So what we can do is, when we have terms like that, especially with on the other side 2 factors, what we do, we're going to simplify this part to the right side to one expression. So let's do that. So that we can take the common denominator, and once you take the common denominator, what do you get? So the common denominator is s plus 1. So that means you have to multiply the first term with that. So it is s plus 1. Here the missing term is only s plus 1. Here only the missing term is s. Okay, so that's what you get, and then you can simplify. Once you simplify, you're going to get what do you get? Negative 4s squared, and then you're going to get we have 7s, 9s minus or 5s, and then we have plus 7. So one single mistake can ruin the whole problem, so be careful with this kind of simplification, especially at the beginning of a problem, because if you have just one coefficient wrong, it can mess up everything. Okay, so we simplify that. Okay, we simplify that. That's a major step. Simplify. Let's try it. So we simplify. Good. Now what we can do, we can divide from this term. So we can divide by that. Once you divide by that, you're gonna get ys equal negative 4s squared plus 5s plus 7 over, look at the two factors. What are the factors of this? So you can see the two factors are s minus 3 and s plus 1. Those are the two factors. So that means this side is going to be, we can divide by that. So you can see you're going to get s, and then we have s minus 3, and we have s plus 1 whole thing squared, because there's another s plus 1 term. So that's what you get. Now what we need to do, we need to invert. Okay, so we almost done. We find the solution in the s domain, but that's not what we need. We need the solution in the t domain. Okay, so we need to invert. Okay, so let's do that. And once you invert, what do you get? So let's try the form. So the form is negative 4s squared plus 5s plus 7 over s minus 3 and s plus 1 squared. And I can see that it is a over s, and then we have b over s minus 3. So this is the repeated root situation. That means c over s plus 1, and then d over s plus 1 squared. So we know that we don't write for the d, we don't write ds plus e, because when you repeat, it's going to follow the format of the smaller one. Good. Now what we can do is we can use the cover up method for this one. So I'm going to use the cover up method for this one. And if you don't know what is the cover up method, you can see a link in the description where we solve some problems using the cover up method. So you can look at that and try to understand that. So let's use the cover up method. So what we're going to do is first let's find a. To find a, what we're going to do, this is the terms. That means we're going to cover up s term. So just ignore s term and substitute for everything else. So what you're going to substitute? You're going to substitute s equals 0, because that's going to make this is going to make that term 0. So we're going to go with that. So that means this is s equals 0. So that's we're going to substitute. So let's do that. So that means a is simply, so using cover up method, a is you're going to substitute. So we're going to substitute. I mean, just go show 1. We can ignore s term, so that means we have negative 4s squared plus 5s plus 7 over s minus 3s plus 1 squared. We're going to substitute s equals 0, because that's the term we that make the denominator 0. So let's substitute that, and once you do that, you end up getting negative 7 over actually 7 over negative 3, so you can write it like that. Good. And similarly, you can find b. So for b, what are you going to get? You're gonna substitute s equal 3 for the other terms. So that means you get negative 36 plus 15 plus 7 over 3 times 3 plus 1 squared. When you simplify, you get negative 14 over 3 times 16, which is simply negative 7 over 24. And similarly, so we have a, b, and so we actually, from the cover up method, you cannot find c. The reason is when you try to plug in s equal negative 1, the other term also going to get 0. So that means you cannot find c, but you can find d. So let's find d using the cover up method. So d is simply negative 4s squared plus 5s plus 7 over, you ignore s plus 1 term, so you have s minus 3. So that's the term you have. You plug in s equal negative 1. So when you plug s equal negative 1, you're going to get negative 4, negative 5 plus 7 over negative 1, negative 4. So that means you're going to get negative 1/2. So that's what you get. Now, unfortunately, you need to go back to and find c, back to the method that we normally use to find c. Or there's another way to do that. What you can do is you can plug in some other value. For example, you can plug in s equal negative 2. Okay, so you can plug in s equal negative 2 and solve. So that's one way to do that. Or you just go back to the regular method and find only c. So you can do that. So that's kind of shaky at this time, because you need to go back to the method or substitute some other value such as s equal negative 2. And if you substitute s equal negative 2, you get an expression and where only thing that you don't know is C, because we already know A, we already know B, we already know D. So just plug in that and solve for C. That's one way to do it. Why we pick -2? Because you can see that when you pick -2, in the bottom you will only get -1. So this is easy to handle. So that's the kind of idea why we pick -2. That always works. Uh, so uh, oh, so just go back to the classical argument and look at the coefficient. So I'm going to go with that also just to tell you. So now I'm going to write that. Okay, so let's say to find C, we can substitute s equal -2. That's a special number because that's gonna make a like a smaller denominator. And then and get an equation. In A, B, C, and D, but we already know A, B, C, and solve for C. That's one way to do that. Or the other way is just use the regular technique and just find C. So if you do that, if you go back to the other method, so what we have is we have -4 s squared plus 5s plus 7 identical to we have a times s minus 3 s plus 1 squared plus bs s plus 1 squared plus cs s minus 3 s plus 1 plus ds s minus 3. Now what we can do, we can use the coefficient technique. We'll use the highest coefficient. Okay, so let's go with the highest coefficient. That means s3. You got s3 term here, s3 term there, s3 term there, no s3 sum from D. So you only have a, b, c in this case. But if you use a substitution technique, you have a, b, c, d. So it's a kind of little easy if you do that. So we're gonna go with the coefficient of the largest term. Okay, so that means null s3 term here, and you have a plus b plus c. Okay, now in this case c is simply negative a negative b. We already know a and b, so plug in them. So a is how much a? So it's a -7/3. B is -7/24, and take the common denominator, which is 24, and then that means you have to multiply by 8. So you have 56 plus 7 over 24, which is 63 over 24. You can divide by 3, so you're gonna get 21 over 8. Okay, so that's the coefficient. So we have all a, b, c, d. Yeah, this one took a little long because it's little difficulty. There's a little difficulty to find c, but it's still doable, but little long. Good. So we get that. Now we have all three. Now what we can do, we can substitute and solve. So you can see that none of them are 0. So now your ys is like this. So this is the ys term. So after you substitute, we have ys, which is simply a -7/3 1 over s, and then -7 over 24 1 over s minus 3, and then 21 over 8 1 over s plus 1 minus 1/2 1 over s plus 1 squared. Okay, that's what you get. Now we can invert. Okay, so by inverting, yt is you're gonna get this 1 over s, that means 1, so negative 7/3, and then we have 1 over s minus 3, so that means e to the 3t, so that means negative 7/24 e to the 3t, and then we have the next one is 21 over 8 e to the, in this case a is 1, so that means negative t from the formula, and then here we have 1/2. Well, now you can see, so this is the shifting theorem. So we have s plus 1, so we're gonna ignore plus 1, so it's 1 over s squared, that means t, and then the shifting part is e to the minus t, and you can see that's exactly what we expected. We expect a solution like that, and you can see that that's exactly what we get. Okay, so that means the Laplace transform also works very nicely, and we get the solution as we expected. Good. So now what we can do is I'm going to show you some special cases that works like nicely without the without even need to find the partial fractions. Okay, so let's do that. So some special cases. So let's say special cases. So one special case is this. So let's say I'm going to say A. If you want to solve y prime plus 3y equal e to the 3t, along with, let's say, just to make things easy, I'm going to say these are all 0. Okay, so if you get a problem like that, we know we can solve. This is first order linear. So this is first order linear. First order linear. So when you have first order linear equation, how we solve it, we can use the integrating factor method. But let's see how we can use the Laplace transform for that. Okay, so for this one, we can use integrating factors. Integrating factor. But let's see how we can use this technique to solve this one. So we can take the Laplace transform. So once you take the Laplace transform, this is going to be, so I'm just writing, taking Laplace transform. So we're going to have s ys plus 3ys. So what's the Laplace transform that? That's the eat function. So that is 1 over s minus 3. That's what you get. The opposite sign always. Opposite sign. And then if you factor this side, you're going to get s plus 3 ys equal 1 over s minus 3. This says that if you divide ys equal 1 over s plus 3 s minus 3, s plus 3 s minus 3, but this is the difference of squares, that means this is s squared minus 9, and we know how to find the inverse of that. That is the hyperbolic sign. You can see only 3 is missing, so you can multiply the top and bottom by 3. So that means it's going to be simply yt is the inverse Laplace transform of 1/3 3 over s squared minus 9. So this is hyperbolic sign. So this is 1/3 sin 3t. So you can see you can just solve it even without finding the Laplace transform here. So you're gonna get that quickly. Yeah, so for this one you don't need the Laplace transform. You don't need the partial fraction technique because it's already there. So let's do another one with the opposite sign and see how it's gonna work. So if you change the sign, okay, good. So I'm gonna say B. We have, let's say, y prime minus 3y equal e to the 3t. I'm going to change that. And then here we have y0 equal y prime 0 equal 0. Same thing, take the Laplace transform, so it's going to be s minus 3 ys, that's what you get, and same as before, this is s minus 3, so that means ys simply becomes 1 over s minus 3 whole thing squared. Now we're going to take the inverse. So this is that the yt is the inverse of 1 over s minus 3 squared, and we know that this is the shifted version, so we can ignore negative 3, so it is 1s squared, which is t, and then because of the negative 3 you have to multiply by the e to a function, but its opposite sign is a negative 3, that becomes positive 3, so that means e to the 3t. So that's the solution. But again, you don't need to find the partial fraction for that, so solution directly comes like that. So these are special cases. And how we normally do this problem is we use the integrating factors, but you can see that the Laplace transform give you the solution much quicker, okay, much quicker for this type of problems. Okay, good. Yeah, for this problem actually you can use the Laplace transform. So you can solve these kind of problems in 4 different ways. Integrating factors work, and then undetermined coefficient method works, series solution works, and then also we have this Laplace transform, which is much quicker. Good. Yeah, actually I have solved that in another video, so you can look at that, all 4 techniques to solve one problem, and then you can compare how it works. Good. Now the next topic, you see that this is like a little long because there are a lot of things to discuss. Next topic is what we're trying to do is what other things come into play. For example, we can use a shifting theorem for problems to solve these. Okay, so let's call using shifting theorem. Using a shifting theorem. We already know what is the shifting theorem. We discussed that in the inverse transform video. For example, we know that the Laplace transform of e to the minus at ft is simply f s plus a. So we know that. So this is gonna work when s plus a positive. So this is what we call a shifting theorem, and this is very easy to prove. So what we're trying to do now is let's try to use this theorem in a problem. Okay, so the next example is gonna be like this. So let's start with this problem. So I'm gonna go with I'm gonna go with this one. So solve. Let's say y double prime plus 2y minus 3y equal t e minus t, along with y0 y prime 0 equals 0. So you can see we have the special term here. So when you want to find the Laplace transform of that, you have to use the shifting theorem for this. Okay, without that, you can use the like a basic definition, but the shifting theorem will be much faster. So that means you need the shifting theorem to solve problems like that. Okay, so let's use the shifting theorem and write the formula you get. Okay, so the taking Laplace transform. So we have s squared, and you can see all the initial conditions are 0, so that means you only get this s term, so s squared, so you get the characteristic equation in s, so plus 2s minus 3 ys, so that's the transform solution, ys. On the other side, you use the shifting theorem, so that means if you take the Laplace transform of t, it is 1 over s squared, but you have to shift it by plus 1, okay, because the opposite sign plus 1, So that means in this case it is simply 1 over s plus 1 squared. So that's what you get. So that's the transform solution. That's the transform of the non-homogeneous part. Okay, now what we can do, we can look at the factors of this. So what are the factors? So the factors are s plus 3 and s minus 1. So those factors, so we can divide by that. So let's see what's going to happen when you divide. So you can see, so you're going to get ys equal 1 over s plus 3, and then we have s minus 1, and then s plus 1 squared. So what we can do is, so we're gonna kind of, I mean, there's an obvious way to do this one. So we see the factors, write the partial fraction decomposition and solve it. But we can talk about a special factorization for this one, since this is the Laplace transform problems and we know a special format. For example, whenever you see a denominator like this, we can, whatever the top has to be the s or some constant. So but when you see this kind of special denominator, when you see this kind of special denominator, I'm going to put a box there just for the top. We can kind of use a different partial fraction technique. Okay, so we can use a different partial fraction technique because we try to see whether we can create that term. So that means what we're going to do is we're going to combine this into one of them. Okay, that's how we do. So we're going to look at this special factorization. So I'm going to pull out s plus 1 and we can write this one in this form. So we can write this one as, so let's say we can write this one as 1 over, we still have s plus 3. I'm going to pull s plus 1 out. I'm going to pull s plus 1 out and I'm going to combine the rest of the one with that. So that means you're going to get s squared minus 1. Why we do that? Because you can write the solution using the hyperbolic sine or cosine. Okay, because we already know the solution. So that's why we use that special factorization. And remember by that, we can always do that. Okay, so this is the kind of idea happening here. Okay, now let's try to write the partial fraction form for this one. So you have to be careful how to write the partial fraction. So when you write the partial fraction, so it's clear we have s plus 3, so that means we have a over s plus 3 term. And there was a next term, because we can always combine s minus 1 and s plus 1 to create the third term, s squared minus 1 term. But what about s plus 1? See, there's an extra s plus 1, but that means there is always a term s plus 1 squared inside that you cannot avoid. So that means there is a term with b s plus 1 squared. Please remember that. That's the reason, because you can see if you look at the original, factorization, you see the s plus 1 squared term. So that's there because there's no way you can absorb that to any other term. But you can absorb s minus 1 and s plus 1. So so these two terms you can always absorb. Okay, whatever on the top, s minus 1 plus something s plus 1. See, you can always combine these two to create one term with the s squared minus 1. So that's the term we are writing next, because we can always do that. So we have a square, so you don't need to write two terms for that for Laplace transform technique. But if you want to do integration, you might need to do the other one. Okay, so and then here is squared minus 1, and we don't know what the top look like, so it is cs plus d. Okay, so that's a special factorization. Okay, so this is special factorization. Special partial fraction, special partial fraction. So you can see, so we can use the structure of the Laplace transform to write that. So that's gonna give you answer much quicker. So that's why we do it like that. Okay, good. But you can still do the other way and later combine, but this is much faster. Okay, now we can write the goal is to find ABCD. Okay, So we write the form. Form is 1 identical to from the first one you're going to get a times what is the missing term? If you look at the common denominator, the missing term is s plus 1 is missing, and then s squared minus 1 is missing. And for b, you can see s plus 3 is missing, s minus, okay, what is missing there? If you look at the s squared plus 1, if you look at the first one, you can see s plus 3 and s minus 1 is missing. And then the last one, cs plus d, s squared minus 1 is there, so that means we have so s squared minus 1, so we have s plus 3 and s plus 1. So s plus 3 and s plus 1. Okay, good. So those are the terms. Then we can use try to use the substitution method first and see whether you can find some, and then use the coefficient method. So I'm going to go with the substitution s equal 3, negative 3. So let's do that. So I'm going to go with the substitute s equal negative 3. So once you do that, 1 equal, you're going to get 8 times. If you put s equal negative 3, the other two terms get cancelled. So you get negative 2 and 8. This can give you a, which is negative 116. And then you're going to go with the substitute s equal negative 1, because you see that s plus 1 term. So it's going to give you b. So that means again 1 equal b times 2 times negative 2. So this is going to give you b, so which is negative 1/4. So we already know 2. And then we're going to go with the we're going to substitute s equal 1. So, and you can see there are no other terms that you can substitute to get something directly. So we're going to substitute s equal 1, and if you do that, you get 1 equal c plus d times 2 times 4. So this only give you an equation. So we're going to get c plus d equal 108. Now to do the rest, what you need to do is, let's go with the coefficients. So I'm going to go with the coefficient of s3, the highest one. So let's go with the coefficient of s cube. If you do that, you get 0 equal, how to get the s cube? This is s cube, no s cube, and this s cube here, this, that, and that. So that means you're gonna get a plus c. So those are the coefficients, but we already know a, so this says that c has to be the negative, the opposite sign. So that means it is 1/16, and then once you know c, we can find, so this is that d equal 1/8 minus 1/16. That's a half of 1/8. That means you get the other half, so 1/16. That's the d. So we find all four. Okay, not that long, but here we use a special partial fraction technique. We leave a term like that because we already know the inverse of that. So that's the kind of secret here. Okay, so let's continue. Now we only need to invert because we already know the fractions. So let's write the fractions now. So what we get, so your ys looks like this. So the ys is simply we can substitute. So you can see that a is negative 116, so it's negative 116, 1 over s plus 3, and then b is, how much you get for b? Negative 1/4, so it's a negative 1/4, 1 over s plus 1 squared, and then we have a c and d, they are the same, 116. So we can do that. So that means and also you can split, so it is 116 s plus 116 over s squared minus 1. But what we do is we can split that into 2. So this step is not necessary. You can directly write this one. It's up to you. if you see that. Okay, so it is s plus 3 minus 1/4 1 over s plus 1 squared, and then here we can split this 1 over 16 s over s squared minus 1 plus 1 over 16 1 over s squared minus 1, and then we know the forms of all four, so let's write the invert. Okay, so by inverting, we have yt which is equals to the first term says that it is negative 1 over 16, the opposite sign, e to the negative 3t. The next one is 1 over 4. The shifting theorem is 1 over s squared, that means t, and also e to the minus t. So this is, we use the shifting theorem here. Okay, because 1 over s squared. What we normally do is we ignore that part. And try to figure out what the term. And once you know what's the term, in this case 1 over s squared, that means t, and then you just write the shifting part is opposite sign always. Okay, and then we have 1 over 16. This is the one with s, that means a cos. Omega is 1, so it's a cos t, and plus 1 over 16, that's a sin. Omega is 1, so it's a sin t. Okay, so that's what you get as a solution. So what I will tell you, we use a special partial fraction decomposition here. Okay, and as the next example of this type, I'm not going to do all this time. I'm going to leave something for you. So let's do this one just to show you what's out there. So solve, let's say y double prime plus 2y prime minus 3y equal, let's say something like this: 4e negative 2t sine 3t, and again let's say let's put the coefficient to 0. So let's say y 0, y prime 0 equals 0. So let's put those to 0 just to make the calculation simple, little simple. Okay, good. Now again, because of this term, so we can use a shifting theorem. Okay, so so let's say using the Laplace transform and shifting theorem, using Laplace transform and the shifting theorem. So what will happen is, so you can see this is s squared plus s squared plus s minus 3 times ys equal. So what do you get on this side? And you can see this is a 4. What we do is we look at the transform of sign and then shift by s plus 2. Okay, we simply replace s by s plus 2. So doing that, we know the Laplace transform, this one is 3 over s squared plus 9, and because of that we can write 3 over s plus 2 squared plus 9 because of the shifting. So if you simplify this, you're going to get 12 over, you're going to get s squared plus 4s, and then we have 2 squared means 4 plus 9 means 13. So that's what you get, and then you can divide, and we can write the partial fraction. So let's write the first few steps, and then by dividing, and okay, what are the factors of this one? So let's see the factors. So s, we have minus, so that means plus, you can have s plus 3, yeah, so it's a 3 there. So that means if we have s plus 3 and s minus 1. Oh, actually I had a different, yeah, there's a typo there. So this has to be 2s. Yeah, so this has to be 2s. So that means the factors are s plus 3 and s minus 1. So that means we can divide by that. So then we're gonna get the transform like this. So now the y's can be written as ys equal, we have 12 over the two factors s plus 3 s minus 1, and then we have s squared plus 4s plus 13. And you can see that this can be written in the partial fraction form as a over s plus 3 and then b over s minus 1 plus, so you can see you can factor the other term nicely, so we leave it like that for s plus 13, and this can be cs plus d. So I'm going to let you find ABCD using the regular technique that we have already discussed. So you should get solving uh, you're gonna get solving for A, B, C and D. You get A equal negative 3 over 10, and then B equal 1 over 6, and then C equal 2 over 15, and D equal negative 89 over 15. So those are the four numbers that you get, and then you can write the then you can substitute and you can write ys. So the ys is going to be negative 3 over 10 plus 1 over s plus 1, and then 1 over 6, 1 over s minus 1, and then what we have, you can see 2 over 15, 89 over 15, so I'm going to take 1 over 15 out, and then you have the rest is what you have is you have s squared plus squared plus 4s plus 13, and you can see you can rewrite this one as, so we need this s plus half of the coefficient squared, then you can see you're going to get s squared plus 4s plus 4, but 13, that means 9 left, so you're going to get that, and that's exactly what we're going to use here. So I'm going to erase that part, so let's put that, so that means this is going to be s plus 2 squared plus 9, that's simply coming from here, and then what you're trying to do is you try to create the same term at the top. So that means what you have is you have 2s, you have 2s minus 89. So how you're going to do is you're going to handle that, we're going to say 2, we're going to create the s plus 2 term here so that they're going to match with that, so this is going to match with that, and then once you do that, what do you get? You're going to get 4 extra 4, that means you have to subtract that. That means if you subtract another 4 from 89, you're going to get 93. So that's what you get uh, as a constant term. So this is a kind of trick that we use. You try to write a term to match with that. Now what we can do, we can split them into two. So let's do that, and then we can take the inverse. So once you so I'm going to rewrite them. It's a 3 over 10 plus 1 over s plus 1 plus 1 over 6, 1 over s minus 1 plus, so what we have here is 2 over 15 s plus 2 over s plus 2 squared plus 9 minus, and then you can see that the other term is 93 over 15, so that you can actually take 3 out, so we can write this one as 31 over 15, and then 3 over s plus 2 squared plus 9. 9 means 3 squared. Okay, so that's exactly why we leave 3 here, because this is 3 squared. Good, now we can invert. So by inverting, we have yt which is simply equals to negative 3 over 10. This is plus 1, so it is minus 1t. And then this is a minus 1, so it is plus 1t. And then for the next one, you can see this is the uh, cos version. So this is the cos 3t, and this is the sine. Okay. So, but with the shifted version, you shifted by like plus 2. That means you have to multiply by negative e to the 2t. Okay. So you're gonna get. So we can write that. So the coefficient is 2 over 15. The shifting term is e to the negative 2t. That coming from that. So that's that term gonna give you that. The plus 2 gonna give you that. And then we have this is the cosine, so it's a cosine 3t, and then negative 31 over 15 sine 3t. So that's the solution for this differential equation. Okay, so let's also look at what's there. I mean, what is this differential equation? Let's go back to the differential equation. We can see we had so I'm going to write the equation that we have. So we start with so it's like a small note. So you can see we have y double prime plus 2y prime minus 3y equal 4 e to the negative 2t sine 3t. So what is this? Actually, we're gonna get these kind of problems when you try to solve what we call the mechanical vibration problem that we're gonna discuss in another lecture. So so what we have is we put a like kind of let's say mass on friction uh, uh, surface, and then we also have a spring attached to it. So we're gonna put a spring attached to it, and then we're gonna put an external force there. Uh, so this is the kind of system that we have. So we have a mass on a friction. So there's a friction on the ground on a surface. So I'm gonna mark the friction like that. It's not smooth. And then we're gonna put external force. So the external force, we can say the input force. We normally call the IT. So the input force is given by that function. So what the input force looks like? So input force, you can see that's the decay function. It's gonna, because of the e to the negative 2t is gonna decay. Uh, so you can see it's gonna decay like that. It's gonna decay like that, and but it is a sine function. So that means the graph gonna look like 0, and then it's gonna go like that between those two curves. So that's the kind of situation. And then what this says, so if you put such an input function to this mass spring system, this is what we call mass spring system. So the corresponding differential equation looks like that. So that's the corresponding differential equation, and then this is the solution we get. So we're gonna get a this kind of solution for this system. So those are really useful if you are solving problems in engineering. So if you have a mass spring system, and this is what you end up getting. Okay, so that's about that. And as the final problem of this type, I'm gonna do a little like another problem from the completing square method, just to exaggerate the technique. So let's discuss that, and then we do one from a higher order differential equation. Okay, that's the only thing left for us. So let's talk about. So let's do one last problem from completing square method. So completing square method. So let's do this one. Let's say we have y double prime plus 2y prime plus 3y equal 2e to the negative t, along with y0 equal 1 and y prime 0 equal 4, some non-zero constants, initial conditions. So taking Laplace transform, so So taking Laplace transform, we have s squared ys minus sy0 minus y prime 0, and then plus 2 times sys minus y0, and then plus 3 ys. And then what you want to do to transform, that's the eat function, and we remember the Laplace transform of e to the minus at is simply 1 over s plus a, so we can use that here. So that means a is 1 in this case, so it is 2 over s plus 1. Now what we can do, we're going to substitute the values, y0 equal 1, so these are 1, and then y prime 0 equal 4. And once you plug in that, you're gonna get, so you're gonna isolate the ys term. So you have s squared plus 2s plus 3 ys equal, if you bring the other terms, you're gonna get s plus 6, and then we have 2 over s plus 1. Now what we normally do is we're gonna kind of combine all of them into one. So if you do that, just take the common denominator. So then we have s plus 6 times s plus 1 and plus 2. So you can simplify the top. So then you finally get ys equal, so you're gonna get s squared plus 7s plus 8 divided by, we have s plus 1 from here, and then we have s squared plus 2s plus 3. And you can see that you cannot factor this into linear factors, so we can leave it like that. So now we can write the partial fraction decomposition. So writing partial fractions, so we have s squared plus 2 plus 7s plus 7s plus 8 divided by s plus 1 s squared plus 2s plus 3 identical to a over s plus 1 plus, but we have here s squared plus 2s plus 3, so it's a degree 2, so degree 1, so it is bs plus c. So the argument is, if this is degree 2, this has to be degree 1 less, so degree 1. Okay, now what we're gonna do, we're gonna multiply and we try to find the coefficients, so let's do that. So we're gonna write this one as s squared plus 7s plus 8. So you can see that this is the exact same thing we are doing, and at the end we can transform, so it's not difficult. Okay, so a, the missing term, which is s squared plus 2s plus 3, and then on the other side it is bs plus c, we have s plus 1. Now the secret, we always use the substitution first. Okay, so there's a secret. So substitution, we're gonna say is minus 1. Once you do that, you're gonna get 1 minus 7 plus 8 equal 8 times, we're gonna get 1 minus 2 plus 3 plus 0, and this gonna give you the value of a. So what do you get actually? So you can see that I can write one more equation. So you're gonna get 2 on this side equal 8 times 2. In other words, a equal 1. And then, so you can see that you can substitute anything else. So let's go for the coefficient technique. So I'm gonna go with the highest coefficient, which is s squared. Then this is 1 on this side. On the other side, the highest coefficient is s squared, and here you get have b. Okay, so that means it is a plus b. So this says that b has to be 0 because we know that a is 1. That's the benefit. Once you have those other coefficients ready, you can just find the rest. So it's very easy. And then we're gonna go with the You can go with the S term or the constant term. Constant term is easy, so I'll go with that. So 8 equal, the constant is 3a plus c, and this is the c is 8 minus 3a, so that means 5. So we have all three. Now into plugin, so that means your ys is simply 1 over s plus 1 plus b is 0, so c is 5, so 5 over s squared plus 2s plus 3. So now that's the step. So what we're gonna do, completing square, we complete square here. Okay, so complete square. So once you do the completing square, so you end up getting 1 over s plus 1 plus, and you can see s, take the half of the s coefficient square and then try to match. Once you do that, you get s squared plus 2s plus 1, so the 2 is missing. So 2 is missing. So what we can do is we can write that 2 as square root 2 squared. So that's what we did. And then 5 is there. Okay. So now you can see that this is the sine version. So this is the sine. So this is the sine. So that means we can write the and also the shifted version. Sine shifted. You have plus 1, so that means you have to multiply by e to the negative t. So let's write the, so take the inverse. Okay, so taking the inverse, taking the inverse, we have yt is simply 1 over s plus 1 means e to the negative t, and then plus, so you can see on the other one we are missing square root 2 on the top, so we can do that. So that means we can write this one as 5 over square root 2 the inverse Laplace of square root 2 over s plus 1 square plus square root 2 squared. That's what we have. So that means this is simply e to the minus t plus 5 over square root 2 e to the minus t, and then this is the sine. So you can see sine square root 2 t. So that's it. So that's the solution to the initial value problem. So we use the completing square method for that. So that's the completing square part. Okay, good. So what I'm going to do now is I'm going to do just one example from higher order differential equations, and we can see that the same technique, only thing is we can have a little bit more factors to handle, but otherwise it's just the same thing. So let's just do one example just to show you what's going on. So higher order differential equation, higher order differential equation. So let's solve this one. So let's say solve. Let's go with y triple prime minus y double prime minus 4y prime plus 4y equal 3e 2e to the negative t, along with y0 equal 0, y prime 0 equal 1, and y double prime 0 equal 2. So let's go with that. Again, same thing, taking Laplace transform, we have s3 ys minus s squared y0 minus s y prime 0 minus y double prime 0. Okay, so there are a lot of terms, all negative, remember, and then minus we have s squared ys s y0 minus y prime 0, and then we have negative 4 we have s ys minus y0. Actually, it would be better to write them here because there are a lot of other terms, so I'm going to write somewhere here just to manage the space. So let's say we have negative. I'm writing the y prime term. So 4, and then we have s ys minus y0 plus 4ys equal 3. So 3 means it is 3 over s minus 2 over s plus 1. That's what you get. So that's that term. Good. Now what we can do, we can substitute the values that we have. Y0 equals 0, so this is gone. This is gone, and these three terms are gone because it's 0. And then we have y prime 0, which is 1, and then this is 1, and also y prime 2, which is 2. Okay, so let's plug in and then simplify. So once you plug in and simplify, you're gonna get all the ys terms, which is s3 minus we have s squared, and then minus 4s plus 4. So you can see this exact same characteristic equation. You replace lambda by s, and then I'm going to move the other terms to the side. So we're going to get s minus 2, and then we have 3 over s minus 2 over s plus 1. So what you can do is you can combine all of them, and also we can factor. We have to factor this one. So what are the factors you're gonna get? So we use the grouping method. So if you use the grouping technique, you're gonna get s squared s minus 1 minus 4 s minus 1. So that means s squared minus 4 s minus 1. So those are the factors you're gonna get. And on the other side, what you can do is you can factor. So you can combine the other two terms. So once you combine, what are you gonna get? So you can see you can combine these two terms first. So if you combine those two terms, you're gonna get 3s plus 1 minus 2s over the product. So so that means it's s plus 3. That's what you get. So that means you can write the product ys like this. So your ys gonna be s minus 2 over s squared minus 4 s minus 1, and then we have s plus 3 over the whole product. So this is s, we have s plus 1 coming here, and then the other new 2, so which is s squared minus 4 and s minus 1. So now what we can do is actually we can combine these two, and also you can see that we have s minus 2 and s plus 2. So that means that factor gonna cancel out, so you get 1 top. So that means your partial fraction is gonna be here, is gonna be 1 over s plus 2 and s minus 1, and also the other one you have we can write this one as s plus 3 over s squared minus 4 s squared minus 1. And what you can do, you can actually combine them into one partial fraction. So if you combine them into one partial fraction, so you can see you're gonna get So I'm going to do it. So let's see actually what's going to happen here. So you write it. So you're going to get ys. So if you write everything as one fraction, so you're going to get s times. You're going to get s times s squared minus 4 s squared minus 1. And then we have here s minus 2 s plus 1, so that's missing here, and here we only have s plus 3. And if you simplify the top, you're gonna get s3 minus s squared minus s plus 1. In the bottom we have s squared minus 4 s squared minus 1. We write it like that, so this is it's easy to go forward. And but now what you can see in the top, you can nicely factor this because you can pull out s squared, so the top simply gonna be s squared minus 1 s minus 1. That's what you get for the top. And in the bottom we have s squared minus 4 s squared minus 1, and you can see a lot of terms get cancelled now. So you can see s squared minus 1 s squared minus 1 get cancelled, and then you only end up getting simply s minus 1 over s squared minus 4. That's what you get. Now we again use the partial fraction method for that. So let's try to do that. So you can also think of the linear factors if you want. So so I will write that. So it is s minus 1 over s minus 2 s plus 2, which is a over s plus b over s minus 2 plus c over s plus 2. So we're going to use the cover up method. So we're going to say a, which is simply you plug in c equals 0. So it is 0 minus 1 over 0 minus 2, 0 plus 2, which says 1/4. And then we can go for b. We're going to substitute 2 for that. So that means it is 2 minus 1 over 2 times 2 plus 2, 1 over 8. And then c, which is negative 2, negative 1 over negative 2 times negative 2, negative 2, which is negative 3 over 8. So that means the ys is simply 1/4, 1 over 8 s, 1 over 8, 1 over s minus 2, and then we have negative 3 over 8, 1 over s plus 2. So by inverting, we can see that the yt is L inverse ys over 1/4, and then we have 1 over 8, so s minus 2, that means e to the 2t, and negative 3 over 8 e to the negative 2t. So that is the answer for the third order differential equation with some non-zero initial conditions. So only lengthy process is we try to, you need to factor, you have the extra factor in the denominator. Okay, so this is the end of Laplace transform technique, and we discuss various type of problems with different linear factors, first order, second order, third order differential equations. We also talking about the shifting theorem, and also talk about special cases where you don't need the partial fraction technique, and also we talk about a special partial fraction technique that works for Laplace transform method because of the special hyperbolic sine cosine functions. Okay, so this pretty much cover like everything like of this type, and then in the future we're gonna talk about Heaviside function, the convolution theorem.